If you want to highlight the definition of a rational function, it has a function over a function where both f of x and g of x are polynomial functions. So you have a polynomial divided by another polynomial. That makes it a rational function. And now we are going to look at the groups that we had before and do some characteristics of rational functions. Again, off to the side, just so that we have it in our notes, that another word for a whole point of discontinuity, a whole.
Can we just continue calling it that?
You could continue to call it a point of or maybe you want we could call it a pod. There we go. Point of discontinuity, because that's shorter than whole. Okay, so whenever we have non-permissible values, we could have either vertical asymptotes or points of discontinuity. Here we have two non-permissible values in this first example, 3 and -1. What will they be? Wholes or vertical asymptotes? They'll both be vertical asymptotes because nothing simplifies. Okay? If we look at this example, can you see that the x minus 3's would cancel out? And in this case, you are going to get a graph with a hole in it. And since after it cancels out, what equation do you get? You just get y equals x plus 1. So later on, you're going to have to graph this equation at the top. The way that it looks at the beginning is hard to graph, but once you simplify it, hey, that's just a line, y equals mx plus b. Easy to graph. The only thing is we're going to have to label this hole. Where does that hole happen? Well, our non-permissible value, x can't equal 3, so we know the hole happens at 3 comma something. We also know that that hole is on this line. So when x is 3, what's y? 4. That hole will happen at 3 comma 4. So you can find the coordinates of your hole after you've simplified it. Then you can plug that number in and figure out what it's equal to. All right, so example number 1. Use the equations to predict whether it has vertical asymptotes or holes. So again, what we need to do is we need to factor things completely. For A, can you see that you could factor the top as a difference of squares? Our non-permissible value, x can't equal -5. And this one is asymptote or hole? This will be a hole. It's a hole because a point of discontinuity because those x plus 5's cancel out. In fact, if we wanted to, we could now graph this. Because once it cancels out, oh, I don't like that color. Once it cancels out, what are we left with? X minus 5. That's a line. It has a y-intercept here at -5. A slope of 1, so over 1, up 1, over 1, up 1. There's the graph of x minus 5. We now have to go on to this graph and figure out that at -5, 1, 2, 3, 4, 5, there's actually going to be a hole in that graph. And what is the coordinates of that hole? Well, if we plug in -5 into the equation of this line after it's simplified, we get -5 comma -10. And that's the coordinates of the hole in this graph. Now, 2.3 we're not supposed to graph yet, but we'll graph in 2.4. So it's not bad to look at it already and then see it again, because I think you'll learn it better. So this one has a hole. The second one. Woo. Part B, we have 4x plus 2 times x minus 2. Can we factor the top? Yeah, what can we do? Take out a 2. Does anything cancel? No. So this one, the non-permissible value, color code things the same as before, x can't equal 2, and this means that we are going to have a vertical asymptote at x equals 2. Notice notation. It's easy to mix up notation. When you're writing the equation of an asymptote, it's an equation with an x equals. When you're stating a non-permissible value, you say x can't equal 2. So we don't want to have the can't equal sign when we write an equation of an asymptote. All right, so for this one, for graphing, what you're going to find is you're going to have your graph. The first thing you're going to do is put your asymptote in at x equals 2. And then you're going to have to think about, does this one have any other asymptotes? Does it have vertical asymptotes, oblique asymptotes, or neither? And the way that you can figure that out is looking at the highest degree. What is the highest degree in this entire rational function? A 1. Just 1x. So if we look at how many of those we have in the top of our fraction and how many we have on the bottom of our fraction, we get 4x over 4, which is equal to 4. This tells us we will also have an asymptote at y equals 4. Could you find your y-intercept easily on this one? What's it going to be? Plug in 0 for x, -1. What is our x-intercept going to be? X-intercepts are when y is 0, and the only place we have to look at to figure out where y is 0 is in the numerator. So what would make that equal to 0? -1/2, right? So we have those 2 points so far. Now, if we draw our asymptotic behavior, the only thing we would know is it's going to go like this and like this. But we only have values when x is less than 2. So on these graphs, in order to complete the graph, we have to find out, is there going to be graph in this section or in this section to complete our graph? And the way that we'll figure that out is we'll plug in another value. We'll look at what happens when x is 3. If I plug in 3 into my original equation, can you see that I'll get 1 on the bottom, 14 on the top? So I'm going to have the point, where would that be? Right here? Sure. 3 comma 14, way up there? Yes. That looks like 14. 3 comma 14 way up there. If that point is up there, you know that it's in this section and your other part of your graph would be there. So once you have a point in the section, you can sketch the rest of the graph based on that point. Okay. Now, we were just supposed to talk about it. We could use a graphing calculator to see if our graphs show up like we graph them, which is a good thing to do. Questions to practice after example 1? Question number 5.